Great, thanks for coming. So I'll be talking about robustness meets algorithms. So let me tell you at this outset, this talk is about revisiting some of the problems in robust statistics from an algorithmic perspective. So it'll really be about how to design estimators in high-dimensional applications that are both provably robust and computationally efficient. But maybe before I get to high-dimensional robust statistics, let me start off with one-dimensional robust statistics. And actually, before I get to one-dimensional robust statistics, maybe I should just start off with statistics. So in fact, let me tell you about an important family of problems in statistics, which goes back a long time to the founding of the field, which are generally called parameter estimation. So here the setup is that you're given samples from some unknown distribution, but it lives in some known family of distributions. So here you can think, you know that you're given samples from something that's a 1D Gaussian. You just don't know what its underlying mean mu is, or its variance sigma squared. So the basic question you can ask in parameter estimation is, can you accurately estimate these unknown parameters given a relatively small number of samples? Now the answer to this question is a resounding duh, of course you can, because in fact all you'd have to do is you could just use the empirical estimates. So it's known that if I take a bunch of samples and I take the empirical mean, that's going to converge very quickly to the true unknown mean mu. And the same thing is true for the empirical variance, where here x bar denotes the empirical mean. That's going to converge very quickly to sigma squared. In fact, these two estimators, the empirical mean and the empirical variance, while they're part of a much more general paradigm within statistics, which is called maximum likelihood estimation. Those are the maximum likelihood estimators. And the foundations for maximum likelihood estimation were really laid by Pearson back in the 1900s, where he showed that they have lots of wonderful properties that under pretty tame regularity conditions, you can show that not only do they converge to the true unknown parameters, but they do so at the fastest possible rate. And that's called asymptotic efficiency. So there's a really wonderful theory that you can develop around maximum likelihood estimation. So this talk will be focused on a different sort of question that you can ask about estimation, which really is such a basic question that it could have been asked much earlier, but it traces its origins to the work of John Tukey, who asked, well, we know that what's the best estimator when we really are given samples from a 1D Gaussian. But what happens when the distribution we're getting samples from is not actually a 1D Gaussian, but it's merely close to being one? So what happens if there are errors in the model itself? What type of estimators are good in that context? So what I'm going to do first is I'm going to walk you through how the field of robust statistics, which has its origins in Tukey's work and Huber's later works, frames this question. And it's very important to frame it in the right way so that the problem makes sense when you translate it to higher dimensional settings too. So the cartoon looks like this. You start off with some idealized family of models, but then you add some kind of twiddle of noise on top of it. And this little bit of noise means that you change the model somewhat, and you're actually given samples from this green model on the right. That's actually your observed model. And the basic question you can ask is, if you're given samples from this distribution on the right, is there a sense in which you can meaningfully estimate the parameters that you started off with, the unknown mean and the unknown variance sigma squared? So what I'm going to do first is I'm going to make this more precise and define it properly. And then I'm going to talk about some of the standard recipes in robust statistics, things that work extremely well in low-dimensional applications. And then I'll talk about what happens when you bring in computational perspectives and talk about modern high-dimensional problems. So in order to make good on how to define this problem, the first thing that I have to explain is how do we constrain the noise? So what do I mean that the noise is small? So there are a few ways that you can think about this. Well, one way is you can think about that little twiddle that I added to the density function. I could do something like constrain its L1 norm and say that the L1 norm of whatever this function is at most, let's say, O of epsilon. That's one way to make sure that the noise is small in some meaningful way. Now, another equivalent way to think about it is what you can do is you can overlay these two distributions, the idealized model, the actual 1D Gaussian, and the observed model. And they differ by this little twiddle of noise, and you can think about the area between their two curves. These are the regions in which the adversary is making corruptions. Because anytime the green curve dips below the blue curve, the adversary is subtracting some points from that region. Anytime the green curve is above it, he's adding some other points. So you can also think about it in this other way, which is what the adversary is really allowed to do is they're allowed to corrupt arbitrarily about an epsilon fraction of the samples. And those are the samples that land in between the green and the blue curves. Now, in fact, this has a lot of connections to some of the standard models in robust statistics. It's usually stronger. So, for example, there's a very popular one called Huber's contamination model, in which an adversary is only allowed to add samples to your data. This is slightly stronger because the adversary is allowed to delete it. In fact, everything I'm saying will work in the strongest model that you can think of along these lines, is that in fact I'm even going to allow the adversary to look at the samples and then decide what epsilon fraction he wants to corrupt, and he can do so arbitrarily. Now, all these models aren't really going to change the problem. They'll still be about as hard as each other, but I just mentioned this in case you're curious about, what the real model we're working with is. And just so I can introduce a little bit of nomenclature that I can use later on, here I'm going to refer to outliers as the points that the adversary has corrupted. He can move them anywhere he wants, and the inliers are the points that he hasn't, the things which he hasn't moved around. So now the only thing I need to do to make this problem precise now about robust one-dimensional estimation is, now that I've told you how we constrain the noise that we allow our adversary to add, the next question is, in what norm do we want our parameters to be close? Now, the truth is, in one dimension, it doesn't matter so much how you define closeness and parameters, but in high dimensions, it's going to matter a lot, and I'll emphasize that later. But here's a very natural way, is that you can think about what the adversary has done to your distribution as also being with respect to a particular norm. You can talk about the total variation distance between two different distributions, just half of their L1 distance. And then the way to think about it is that what the adversary has really done is he's taken some idealized model, some 1D Gaussian, and he's moved it to any other model that's epsilon close in total variation distance, any model he wants. And so if this is the norm in which we're using to measure closeness of the distributions or to constrain our adversary's power, it's also very natural to use the same norm as what we want our algorithm to be good with respect to. So one way to define our goal is, if we're given samples from something that's epsilon close in TV to being a one-dimensional Gaussian, the natural question then is to find another 1D Gaussian, this orange curve, that's O of epsilon close to the original unnoisy distribution. So maybe we lose an extra factor of 2 hidden within this big O notation. You can also think about it as maybe your observed distribution really is the truth and it's not noise. The idealized distribution of a Gaussian is just some crude approximation to your actual model. And you can think about it as what you're trying to do is within this nice family of distributions, you're trying to find approximately the best fit, provided that there is a very good fit. So those are both two equivalent ways to think about this problem. So now that I've defined both how we can constrain the noise that the adversary is adding and in what norm we want to be close, well, the natural question that might be on your minds is, can we just do everything we did for standard statistics all over again for robust statistics? In the 1D case, when we talked about parameter estimation, when you're really given samples from a 1D Gaussian, courtesy of things like maximum likelihood theory, we know that the empirical mean and empirical variance are the best you can do. So can we just use the empirical mean and empirical variance in the face of noise? Now the answer here is a resounding no, of course you can't. Because in fact, the way that an adversary could arbitrarily corrupt these empirical mean and empirical variance is he could take a single sample, think about adding a little bump out in the curve, and if he adds that way out into the tails of the distribution, if he moves that bump further and further along and sends it to plus infinity, then the empirical mean is going to plus infinity. The empirical variance is going to plus infinity too. So these are in no sense a meaningful estimate for your original parameters. In fact, it's the worst possible thing you can imagine, because a single corruption means that you lose all your guarantees for your estimator. And actually, these were the examples that were originally used in Tukey's work, is that mostly it was an empirical paper in which he studied all of the classic estimators and showed that adding this goal of being robust changed which estimator you think is better than which other one. So that was a neat way to revisit some of the old debates between Fisher and Dilworth about which types of estimators are best. But in any case, if we want to move to high-dimensional robust estimation, we better at least solve this one-dimensional problem first. So if the empirical mean and empirical variance don't work, does anyone have any ideas about what kinds of estimators might work and might be provably robust? The median, definitely, right? because when I take the median, even if I add that bump way out in the tails, it's not going to move the median too far away from what it was before. So the median is one of the classic prescriptions in robust statistics that you should use it instead of the empirical mean. But maybe now here's the harder question. What about the empirical variance? Does anyone have any ideas? Absolute error? Yep, so that would work. In fact, there are tons of things that work. One of my favorites is, well, if the median worked one time, just use it twice. So take a median of medians. So you take your data, you compute the median of them, and for each one, you look at the absolute value of the distance of the sample to the median, and you take the median of all of those distances. That's called the median absolute deviation, but there are all kinds of things like using truncation and Huber losses and what have you. But here's an example of the type of theorem that you're aiming for in robust statistics, putting it all together. This is a folklore theorem, it's one of the main theorems, is if you're given samples from a distribution that's epsilon close to Gaussian, so now it's not actually Gaussian, but it's close in total variation distance, then all you have to do is compute the empirical median and empirical median absolute deviation and plug in those values, and the Gaussian that you found will be O of epsilon close to the original Gaussian. So this is the best of all possible worlds because it's provably robust. If you started off being epsilon close to being Gaussian, you would end up like 3 epsilon close to that Gaussian. It's computationally efficient because you just have to compute the median and the median absolute deviation. And it's also sample complexity efficient. In fact, it requires the information theoretically minimum number of samples. And I should mention this little corrective constant down here. This phi inverse is the inverse of the Gaussian CDF. You need to add some corrective constant just to make sure that even in the noiseless case, sigma hat would be an unbiased estimator for sigma. So this is just some constant factor correction. So this is what you're always aiming for in robust statistics, something that combines sample efficiency, provable robustness, and also computational efficiency. And it's very easy to do in one dimension, but it'll turn out to be surprisingly hard to do in higher dimensions. Now, just to connect this with a bit more of my home community, within theoretical computer science, we would call this problem proper agnostic learning. So it's agnostic because now you're being agnostic to this belief about the distribution actually being a 1D Gaussian. You just want the fact that if it really is close to a 1D Gaussian, that you also find something that's very close. And it's proper because you're required to output something that lives in your original family. It needs to be a Gaussian itself. So are there any questions? Yeah? What if it's not? So here, it's epsilon close to being Gaussian. Yeah, you could do any of those things you want because at the core of it, you're going to have some family of idealized models. And you can think about adding noise and total variation distance to any of those families. And then you can talk about proper learning or proper agnostic learning with respect to this family. So all of these definitions make sense for many different families that you would care about. But the Gaussian story will end up being something that I can tell you a whole heck of a lot about what happens in high dimensions. Are there any other questions? We're going to see that, yeah. So the 1D case will be very special. So actually, the question that I'm really interested in is what happens in high dimensions? So are there provably robust high-dimensional estimators? And the thing you should think about, and I'm going to come back to some experiments later, are that in a lot of modern applications, we're really thinking like genetic studies, which I am going to show you some examples of. You're thinking about things which have like tens of thousands or millions or hundreds of millions even of dimensions. So there's a lot of impetus for trying to understand what you can do that's provably robust in these contexts. So in fact, what's the main question I'll be interested in for the first half of this talk will be the same problem that I've already shown you, but in high dimensions. So we're going to be working in D dimensions. So you're given samples from a distribution that's epsilon close in TV to a high dimensional Gaussian. The only difference is that now this mean mu is a vector of length d, and this covariance sigma is a d by d positive semi-definite matrix. But this is what I'd mentioned before, is that you have to be very careful in how you formulate the problem. Because I was very careful to say that the way that we measure closeness between our estimate, the one with mu hat and sigma hat, and the true thing, is using the total variation distance. See, what makes that nice is if I instead think about using other norms. If I have something like, I look at the difference between sigma and sigma hat, and should I measure that matrix in spectral norm, in Frobenius norm, in nuclear norm, those are all different choices that usually differ by some polynomial in d factors. So choosing the right norm prevents you from cheating. My adversary is allowed to move me in total variation distance, so the goals of my algorithm are the same. I want to be close within total variation distance, and it's a nice guarantee that's actually invariant to changing the distribution according to affine transformations. So it has lots of wonderful properties. And there'll be two important special cases that'll help me get it to the heart of what's known and what some of the new results are. So what if I make your life easier? I could promise you that the unknown covariance sigma is actually the identity. That's a spherical Gaussian. I'll call that then the unknown mean case, because your only job is to find what this unknown vector mu is. And another important special case is when I promise you that the unknown mean is 0, and your only job is to determine the unknown covariance. So in the nomenclature of robust statistics, these would be called robust estimates of location and scale, respectively. So I'll study these two problems first and then explain how things fit together. Was there a question? Yep?
Can you say two words why the norm makes such a difference? As long as we are in finite-dimensional space, aren't all the norms equivalent?
Up to poly and d factors. Yeah. So the entire game would be the poly and d factors. So let me get into that on the next slide. And tell me if you still have the question. So let's see what's known within robust statistics. So if you think about the unknown mean case in one dimension, well, the robust estimator was the median. So the first thing you could try in this case, where you just have to figure out the unknown mean in high dimensions, to try and generalize the median to higher dimensions, right? And that's exactly what Tukey did. So it's something called the Tukey median. Now, it's not so important for this talk what the Tukey median is, but let me tell you anyways, just verbally. So the Tukey median, you can define the Tukey depth of a point, which is the largest value k, so that over all projections of your data, that one point has k points to the right and k points to the left. So it's a measure of how deeply inside a cloud of points a given point is. And all you would do is you would take a bunch of samples, noisy samples from something that's close to being Gaussian, and you would compute the Tukey deepest point, not even among your samples, but over all space. And that actually would have really wonderful robustness guarantees. If you started off being epsilon close to an unknown Gaussian with mean mu and covariance the identity, then you would have the guarantee that if you computed the Tukey median on your data, you would be O of epsilon close to where you started from. So that's wonderful. That's the best that you can possibly do. But there's a big gotcha, which is that it's NP hard. So in fact, even though it generalizes the median from the one-dimensional setting to the high-dimensional setting, the problem is that the best known algorithms for it run in time exponential in the dimension. So you literally cannot compute these things beyond dimension, say, 6. Now there's something else I could do, which maybe that was just the wrong way of generalizing the median to higher dimensions. So there's something much more naive I can do, which is I could just compute the median along each one of the coordinate axes. That's obviously doable in polynomial time because that's just d median problems. But there's a big problem with that, which is that it's only epsilon times root d close in total variation distance. Now that's really profoundly horrible for reasons that I'll get into in the next slide. But this isn't the problem that you see in dimension 1. It's a problem that you see in modern high-dimensional problems, that you started off being 1% close to a Gaussian, and your estimator got you 1% times the square root of 100 million. It's not super good. So there are other things that you can do, and you can do this entire experiment for all of the estimators that are proposed in the literature. There's something else called the Sheffe tournament that you could run, which has exactly the same tension. It's wonderful in robustness guarantees. You get O of epsilon close, but you suffer from the same end of the D running time. And there are even more basic things you can do about pruning, because essentially a high-dimensional Gaussian looks like it's a uniform distribution over some thin spherical shell where the radius is root d. So if you just throw away points that are just wildly far away from the others, you would end up getting something that's polytime, but you would lose the same root d factor in your robustness. So I'm not going to do this for all of the estimators, but in our paper we have a long list of all of the ones we know of where we broke them. Sorry, which one?
Basically, the point that functionally replaces the median. So you look at the point
Yep.
that minimizes the sum of absolute distances.
Yeah. So that's also broken. You can get it to be as bad as epsilon times root t. That turns out to be one of the hardest ones to break. But yeah, so we have details in the paper for that, and I'll get into that maybe offline. But so in my field, in theoretical computer science, we love price of statements, right? We love the price of anarchy and all sorts of other things. So maybe this is just the price of being robust. So the state of affairs is that all the known estimators for this basic problem of robustly estimating the mean in high dimensions, they're either hard to compute, we need time exponential in the dimension, or they lose polynomial factors that depend on the dimension in their robustness guarantee. So just to explain why losing polynomial factors is so fundamentally bad, it's because if you think about it, the total variation distance is only ever at most 1 between different distributions. So what does it mean in terms of what's the largest fraction of errors you can tolerate and get non-trivial guarantees? You can tolerate at most a 1 over root d fraction. So as you talk about higher and higher dimensional problems, it's plummeting to 0 very quickly the fraction of corruptions you can tolerate and get any non-trivial guarantee out of it. Or to put it concretely, you can think about applications with dimensions being tens of thousands. It means that even though you know in principle it's possible to tolerate some large constant factor of corruptions that's dimension independent, what you actually get is a much more tame robustness guarantee that best case scenario you could tolerate maybe 1% of corruptions. So, you know, we could actually wonder, maybe this tension is actually fundamental. And this is something that I wondered about for a long time. Maybe robustness and computational efficiency are just at odds with each other. Now, I won't tell you about some of the backstory, but it turns out that there are many different definitions of being robust. There are things like breakdown point, which are even harder to satisfy. And those things actually do have this provable tension. That in fact, if you could be robust with breakdown point, then you are solving an NP-hard problem. So in fact, a lot of these questions about what's the right definition, which are things that people chewed on for a long time within robust statistics, actually are quite intertwined with computational considerations. Because it's not a question of which definition allows you to be the most resilient to a really devious adversary. It's a question of which one also allows you to have computationally efficient algorithms, which I think is a neat way that computational tractability enters the story. So let me tell you some of the main results. These are things which we had a paper in 2016, and then there was a huge flurry of work extending this to all kinds of other models that I'll briefly touch on. But the main result is that there actually is a polynomial time algorithm, so it has polynomial running time, polynomial sample complexity, and what it outputs is something which removes all dimension-dependent factors. So you start off being epsilon close to being Gaussian, and you don't care how the adversary has added those epsilon fraction of corruptions. And the promise is that you're going to output an estimate, which is epsilon times polylog 1 over epsilon close in TV. So other than removing these polylog factors, this is the strongest possible guarantee you could hope for these kinds of things. And one of the other things I want to mention, and this will come through when I tell you some of the details of the algorithm, is that you can actually extend all of these results to weaken the assumption. So it's actually not critical that it be Gaussian. It's just important that it have bounded moments. And whatever bounds on the moments you have translate into some types of robustness guarantees. So you can get things merely by knowing the thing is sub-Gaussian, or even merely having bounded fourth order moments. But then you get things like epsilon to the 3/4 instead of epsilon times polylog 1 over epsilon. And at the same time, there was this really nice work of Lai, Rao, and Vempala that studied roughly the same question. So if you translate their results to our setting, what they imply is that you're going to get close to the true mean in Euclidean distance within, let's say, root epsilon times some polylog d factors. And then you're going to be close in Frobenius norm within about a root epsilon factor. So remember that using these types of guarantees which are not affine invariant is a little bit more tricky. But if you translate them to the total variation setting, if you have bounded covariances, what they really translate to is they're getting about root epsilon close within total variation distance. So one of the neat things is that I'm going to tell you not just the way to solve this problem, but a general recipe for how you should approach high-dimensional robust estimation. And it turns out that once you have this recipe, there's a ton of other things that you can do with it. So afterwards, there were works that showed that you can handle more errors. So what happens if an adversary is allowed to corrupt more than half of the data points? Well, it's kind of hard to even define what you want to do then, because the adversary could just create an entirely new Gaussian. And how would you know which one is the right one? But if the adversary is allowed to corrupt 90% of your data, you instead ask the question in the formulation of list decoding, where you want to output maybe 10 hypotheses, one of which is close to the right answer. That turns out to be possible. You can do lower bounds against certain types of algorithms and show that actually removing all of these polylog factors ought to be hard, that there are tensions between computational complexity and robustness when you talk about restricted families of algorithms like SQL. There are, as I mentioned, ways to weaken the distributional assumptions. There are ways to combine notions of sparsity. So what happens when I know that the unknown mean mu is sparse? Can I get better sample complexity guarantees that depend on the sparsity pattern while simultaneously being robust? And there are even ways to work with even more complicated generative models, things like mixture models, independent component analysis, principal component analysis, all sorts of fancy extensions. So I'm not going to mention any of that, but instead what I'm going to do is I'm going to tell you how to solve at least these basic problems about robust estimation of the mean and covariance. So what I promised you is that actually there's one overarching recipe, which is going to be at the heart of how to do robust estimation in high dimensions. And this is the recipe. So I'm going to show you how this recipe works in two specific contexts, and then we'll see how to put the pieces together. So it turns out that so the way this recipe is going to work is that I'm going to find some other parameter distance, which is equivalent to total variation distance for Gaussians. And then what I'm going to do is I'm going to do something much more naive than something like a Tukey median or what have you. Instead, I'm just going to use the empirical mean. We know that that doesn't work, but instead what I'm going to do is I'm going to be adaptive and figure out when the empirical mean has been compromised and use that to detect where the adversary has added corruptions. And that's the key step, is really we're either going to be able to find good parameters by this empirical, this naive estimator, or we're going to be able to purify our data set by removing a lot of the corruptions that the adversary has added in order to mess up our moments. So let me explain how this recipe works, even in the simple case of just the unknown mean, where the covariance is the identity. And we can see how this thing works. Now, all of these steps turn out to be quite formulaic, other than this question about how to detect when an estimator is compromised. That's the main step. But the first step in this case of this unknown mean is the total variation distance is a really nasty distance to work with. It's the right one in a lot of senses, but we want to figure out some other way to measure closeness of parameters that's good enough. So we want to find some other appropriate parameter distance which is just as good. And what I claim is that if you have two Gaussians with the same identity covariance, that you can bound the total variation distance between them by the Euclidean distance between their means. Now, this is very intuitive because if you think about it, well, wherever mu is, wherever mu hat is, it's really a one-dimensional problem because off of that one direction spanned by the difference between mu minus mu hat, everything is the same. It's a standard Gaussian. And along this one direction is the thing that contributes to your total variation distance. In case you're curious, the way that you prove this is pretty standard. What you use is you use something called Pinsker's inequality that relates the KL divergence between two different distributions to the TV distance. And it turns out that there's a well-known formula for the KL divergence between two Gaussians. When you plug it in and use Pinsker, you get exactly this inequality. But what this really tells us is that now our goal of getting dimension-independent robustness guarantees in high dimensions really amounts to getting dimension-independent guarantees for the Euclidean distance in this unknown mean case. It'll be more complicated for the covariance. So now what we want to do is we want to get O tilde of epsilon close in Euclidean distance. And let me explain how these ideas work with a picture. So remember, our idea is going to be much more simple-minded than any of the other estimators that were out there. What we're going to do is we're going to try and use the empirical mean anyways. We just want to detect when it's been compromised. So the way to think about this is that a high-dimensional spherical Gaussian, what it behaves like is the distribution is essentially uniform on some thin spherical shell. Now, what's the radius of that sphere is about root d, because that, if you take a random sample from a high-dimensional Gaussian, will be the Euclidean norm of a point. It'll be, you'll have very tight concentration bounds through things like Chernoff and Bernstein. So if you think about it in this cartoon picture of all of my data is uniformly distributed over some thin spherical shell of radius root d, then how could an adversary with some bounded budget of an epsilon fraction of points really corrupt the empirical mean? All they would have to do is choose some direction, shoot off in that direction, and add a bunch of corruptions right along that shell. Now the fact that the radius is root d and you're corrupting an epsilon fraction of your data moves you by epsilon times root d. So that's fundamentally where this tension was between either we had strong guarantees from Tukey's median, but they were computationally intractable, or we had computationally tractable estimators that only got epsilon times root d, is essentially they weren't able to do anything better than pruning points that are outside of this thin spherical shell. So it's the most naive type of thing that you can think of. But here what I claim is that if the adversary really has moved the empirical mean that drastically in some hidden direction, there actually is a way to detect that the adversary has corrupted our data, that he's tampered with things, because it comes down to the second moment. So the only way that the adversary could have really drastically affected the empirical mean that way is if he affected the empirical variance along that direction too. Whatever direction he moved mu hat along, if you look at that one direction, the variance is going to be much, much larger than 1. And we know that that shouldn't be the case if our data really was coming from a spherical Gaussian. So this now becomes exactly the approach that we're going to try. This is the formal key technical lemma that's at the heart of it. I won't prove this, but I'll explain it. So the way that this works, it's pretty easy to prove, is that if you take a bunch of samples from a distribution that's epsilon close in total variation distance to a spherical Gaussian, n of mu I, then what you can prove is if you take the empirical mean mu hat and the empirical covariance sigma hat, where this is with respect to the empirical mean mu hat, well, if mu hat is really far off from mu, if the adversary has moved you by more than epsilon, he's moved you to 100 epsilon root log 1 over epsilon, then it implies that the empirical covariance is off from what it should be too, that there's a direction of noticeably large variance, that instead of having spectral radius of 1 for the empirical covariance, it's at least 1 plus c prime epsilon log 1 over epsilon. So that's the key idea, and this is all that's going to be used in this and in all of the later works, is the simple idea that in order for an adversary to be able to corrupt the first moment, there needs to be some echo of what he's done in the second moment. And that happens for a lot of other generative models. You just need to work with different types of moments. So how would this fit together to actually give you an algorithm? So now I claim the algorithm is pretty simple, actually. I'll call this a win-win algorithm, because what you do is exactly as I said in the recipe. Either you're going to find good parameters because you computed the empirical mean and it is close to the true mean, or you're going to know that you're in danger. And the empirical mean might be really off from the true mean, but you're going to make progress along a different axis, which is you're going to figure out some way to remove points that you're removing a ton of the outliers that the adversary has added. So you're purifying your set of samples. So what do? So you compute the empirical mean, you compute the empirical covariance. If the empirical covariance is close to the identity, then you know that you're done, because the adversary couldn't have moved mu hat too far from mu. You're done. What if you're in danger and sigma hat really is far from the identity and spectral norm? Well, what would you do? All you would do is you would take the direction of largest variance. So you would take the top singular vector of sigma hat, and when you project along the data, along that direction, what you can show is that the reason the variance is noticeably larger than 1 is because of the corrupted points. So what you can show is that there's a way to find some threshold t, so that if you throw out the points above this threshold t, well, you might sacrifice some inliers here. Those are the black points. But for every inlier you throw out, you're going to throw out at least 2 outliers. And in that way, you're actually reducing the fraction of outliers that are in your current set of samples. So this is a win-win analysis, is that either we have certifiably good estimates for the empirical mean because the empirical variance is what it should be, or we're going to purify our set of samples by throwing out more corrupted than uncorrupted points. And eventually, we're going to run out of corrupted points to throw out. So at that point, we really are going to have good estimates of the true parameters. Now, this actually ends up being quite a bit more technically challenging to actually analyze this thing. So this paper was actually 120 pages, which is fairly long. But one of the reasons it's so complicated is because of all of the nasty things that can happen. See, what happens in the first stage when the adversary adds the corruptions, now in the second stage, even the inliers, the things that the adversary hasn't corrupted, are actually skewed based on the corruptions that he has added in the first phase. Because the corruptions he's added could have skewed which of the inliers you ended up throwing out. So you no longer even have independent samples along the inliers. So you need to do a lot of work to make sure that you can still get good concentration bounds for the types of statistics that I'm talking about here, even over many iterations of the algorithm. It involves things like understanding concentration, Gaussian concentration over linear threshold functions, and other polynomial threshold functions when we get to fancier cases. But what I really want to mention is that actually in that unknown mean case, it turns out that there are a whole ton of things that could have worked there. So in fact, our paper was the merger of two independent groups solving the unknown mean case together. And we had very different techniques for doing so. But it turns out formulating the right recipe to explain what it is you're doing and how the different pieces fit together is really essential when you talk about the fancier cases, especially the unknown covariance. So I want to tell you a little bit about that because that's really where this abstraction of having this recipe in place really pays a lot of dividends because things are quite a bit more complicated there. So let me try and do the same thing in the unknown covariance case. I know the mean is 0, but I want to estimate the unknown covariance sigma. So the first step in my recipe is I want to figure out some other distance between the parameters that's a good proxy for the total variation distance. Now here it turns out to be a little bit funnier than just using the Euclidean distance like we did in the unknown mean case. So I can do the same basic thing that I can use Pinsker's inequality and use the closed form for the KL divergence between two Gaussians. But what you end up doing is you end up using this very funny looking norm right here. You can prove that the total variation distance between two Gaussians with the same mean 0, but different covariance matrices, is roughly the Frobenius norm between I minus sigma hat to the minus 1/2 times sigma hat to the minus 1/2. Now that looks a little bit funny the first time you see it, but I claim that this really is the right way to measure the distance between the parameters. So if you think about it, let's make our life easier. Imagine that both sigma and sigma hat were diagonal matrices. So what this is really doing is this thing on the right-hand side is penalizing you based on the ratio of the variances along any of the directions. So any variance where sigma is really, really tiny has to be a direction where you really have to get the right answer, otherwise your total variation distance is going to be large. And that's exactly the right way to measure in parameter distance the distance between two different covariance matrices. This is usually called the Mahalanobis distance. It's proven through Pinsker again. And that's not something you might have guessed at the outset. So if I'd chosen the wrong way to measure the distance between parameters, I looked at sigma hat minus sigma in spectral norm and Frobenius norm, it might have been very easy to hide those dimension-dependent factors that I'm really interested in getting rid of in the way that I've defined my problem. In any case, this is now our goal, is to try and get epsilon close in this Mahalanobis distance instead. So this distance is strange, but I do promise you it is the right one. And now let me give you a little bit of a sketch about how to detect when the empirical covariance has been corrupted, because this is where some of the fancier math comes in. So I promise you it's only 2 slides and then we'll get to experiments, but indulge me. So what if we are actually given samples from a Gaussian with mean 0 and covariance sigma? Now, how do we detect when the naive estimator, just the empirical covariance, has been compromised by an adversary who's allowed to corrupt an epsilon fraction of the data? So what I claim is this key fact right here. So imagine that just the same way in the empirical mean case, we want to detect the corruptions in the first moment by going to the second moment. So here we want to detect corruptions in the second moment by going to the fourth moment. But the trouble is that the fourth moment is hard to work with algorithmically because it's a tensor optimization problem. It turns out there's a way to turn it into a matrix problem, and this is a little bit subtle. But imagine I give you samples from n of 0 sigma, these x sub I, and I represent its fourth order moments as a d squared by d squared matrix. So I take the expectation over the samples from the distribution of xi tensor xi, and then I take it times its own transpose. That's a d squared by d squared matrix. When I take the expectation, what I claim is that that matrix has a really nice form when you're talking about Gaussians. That if you restrict this matrix, this d squared by d squared matrix, to acting on only the right subspace, namely the flattenings of d by d symmetric matrices, that it has this really nice, clean, closed form expression right here. So I should tell you what the symbol right here means, this flat. It means you flatten it. So that's the flat symbol, right? So what you do is you take this d by d matrix sigma and you flatten it into a length d squared vector, and you take it times its own transpose, and that's the third term. So I'm not going to prove for you where exactly this comes from in case you know these kind of things. It's usually proven through something called Isserlis's theorem, which is something that comes up in quantum physics, and it has to do with the relationship between the moments of a Gaussian and the matchings, and perfect matchings. But one simplistic way to think about it is that if I think about a Gaussian in 1D, n of 0, 1, then actually its fourth moment is 3. Now you can take that as a fact, and there's actually a much more pedantic way to say that the answer is 3. It turns out that if you take a complete graph on 4 nodes, there are 3 perfect matchings. And that's the reason why its fourth moment is 3. And you can generalize that connection. So if you think about higher dimensional moments of 1D Gaussians, the moments are always the number of perfect matchings in a complete graph. And that same connection, that's Isserlis's theorem, extends to higher dimensional Gaussians too. That the way that you can compute the moments is actually based on a sum over perfect matchings. But the way to think about this term right here is that it's expressing the fourth moments of a Gaussian. And there are really 3 terms, because there are 2 terms that look like sigma tensor sigma, and there's one term that looks like this. And that one term, the reason it comes from is because if you think about it, I've flattened a d by d by d by d tensor into a d squared by d squared matrix. But one of those matchings is a little bit different than the other. The matching that pairs 2 things that are on the same side of the flattening actually behaves differently than ones that pair an xi with something on the other side. So that's exactly where the notion of matchings comes in to show this kind of structure. Now, but if you think about this, the really big problem with this is that imagine that I plugged in sigma as the identity, just for simplicity. Then the identity tensor with the identity is just a big identity. Spectral norm is 1, no problem. But I flat now is a rank 1 matrix, I flat transpose. So its spectral norm has a Paulian d factor when you compute it. So in fact, the spectral norm is really large of m. So it would be really easy for the adversary to add a ton of dimension-dependent corruptions that hide in the shadow of this term. So you need to get rid of that term if you want to remove the dimension-dependent guarantees. So it turns out that there's a way to project out this term, and instead it's through something called the restricted eigenvalue computation. So this is my last very technical slide. But what you're going to do is you're going to transform the data, and you're going to look for large restricted eigenvalues. So you compute the empirical covariance, sigma hat, and then you apply sigma hat to the -1/2 to your data. Now, if sigma hat really were the true covariance, then the distribution of the yi's would look like n of 0i, because you've just made it isotropic. And what you do is you compute this matrix that encodes the fourth order data. But there's a way that you can look for large quadratic forms on it that remove that sigma flat term. I can tell you more about that offline if you're curious. And that ends up being the test that, if it has large restricted eigenvalues, then you know that the adversary really has noticeably corrupted the fourth order moment. And you can use that to find a space of degree 2 polynomials, which actually look much larger on the corrupted data than on the uncorrupted ones. So it's the same basic paradigm, but using some tensor spectral techniques and some of these ideas like Isserlis's theorem. So now I can tell you at least how this would turn into the overall algorithm. So imagine I wanted to solve the fully general problem, which is you're given samples from a distribution that's epsilon close to an unknown Gaussian, but now you don't know its mean and you don't know its covariance. I claim we can actually do it just by fitting together the 2 pieces that I already talked about. So the first thing that you can do is you can use the doubling trick. So instead of taking n samples, you take 2 times n. You pair up the samples and you take xi minus xi prime. Well, if each one of those is a noisy sample from n of mu I, then together xi minus xi prime is a noisy sample of n of 0 to sigma. Maybe I've doubled the rate of noise, not a problem. But now I can use the algorithm for the unknown covariance case to estimate the covariance, and I can find sigma hat. And when I apply this sigma hat to my data, what's going to happen is you can show that if sigma hat is close to sigma, then what's going on is that your new data after this transformation of applying sigma hat to the minus 1/2 is you're getting noisy samples from a Gaussian whose covariance is now the identity. So this is actually a form of a robust version of putting something in isotropic position that's resilient to an adversary corrupting some fraction of the data. And now you can apply the algorithm for the unknown mean case. It turns out you're going to learn with respect to this new distance function right here with sigma hat to the minus 1/2. But that's actually the right distance function because, in fact, if you think about a general Gaussian, in the coordinates where you have really tiny variance, that's where you need to get the mean exactly right. And that's why you're dividing by something proportional to what its variance is. So that gives you the overall algorithm. Now, one of the things that I think is really neat is that robustness is something which is oftentimes in the air. It's something that we talk about a lot. We argue about which algorithms are more robust than other ones. But really the irony is that this field which was designed to talk about these issues, robust statistics, hasn't actually been able to come up with computationally efficient and also provably robust estimators in high dimensions. So most of the theoretical foundations that robust statistics laid back in the 1960s with Tukey and Huber are not things that we can use and apply in our insights in what's happening in high dimensional data analysis. So in fact, when you talk about experiments that test out how robust algorithms are, there are a lot of surprises, things that people take for granted or on faith that they're robust because they seem to be in low dimensions. That actually really goes out the window when you talk about high dimensions. In fact, when we started this, I couldn't find any example of a paper studying the empirical robustness of proposed estimators beyond dimension 6. So we just had no experimental evidence to understand which ones were and weren't, which ones are NP hard and you can't run them in high dimensions, which are heuristics that only work well in low dimensions, and which are things that hide big dimension dependent factors. But let me show you some neat experiments that show you a bit about what the state of affairs was before and what these types of new techniques buy you. So these experiments will come in a few different levels. The first level will be synthetic experiments. These are ones where I generate my data knowing that they really are from a noisy Gaussian. So then there is a baseline truth that I've used to generate the data, and I can check how well you get compared to that baseline truth. So I can generate samples from this unknown mean case where the underlying Gaussian has an unknown mean mu, and the covariance is the identity, and I can add my own favorite 10% of noise. Now at first I thought we had to be really fancy about how we chose how to add the noise to mess up the existing algorithms. My first inclination was, let's add the noise as a Cauchy distribution. Because the Cauchy distribution doesn't have moments, so if you don't remove it, you're not even going to get an estimator which converges. It turns out that you can do much more simplistic things and break all the existing algorithms. All you do is exactly the corruption model I told you. You choose some random direction, you shoot off in it, and you add a bunch of noise right on the boundary of that thin spherical shell. And what that does is there are very popular things like RANSAC, which was proposed in the 1970s. And it has, I think, 10 or 20,000 citations. So it's something which is incredibly popular in principle. But you can see its robustness guarantees right here that when we measure the Euclidean distance between how well its estimate is compared to the truth, it has this absolutely horrible dimension dependence. Where we're talking about once you're in dimension 100 or 200, it's getting essentially vacuous guarantees for how close it is to the original estimate mu. So these are things which the way that RANSAC works is it randomly subsamples the data, computes an empirical mean, and does that many times, and figures out which of its trials is the closest to the right answer. Now, when you talk about low dimensions, you only need a very small subsample to get a good estimate, so you can afford to take enough subsamples that one of them is pure and avoids all of the corruptions entirely. But when you talk about high dimensions, you need a lot more samples, And then all of a sudden it becomes incredibly rare to be able to subsample and get a totally corruption-free subsample. And this is borne out with how badly the dimension dependence is right here. This was the Lai, Rao, and Vempala algorithm that I mentioned right down here. And this little black curve that almost looks like the x-axis is actually the error of this filtering algorithm that I told you. And you can see that it very clearly doesn't have this curse of dimensionality for how its robustness depends on the dimension. Now we can do even fancier experiments. What about the case of the unknown covariance? Now here you can think about the covariance first as being something close to the identity. That's something which is somewhat isotropic. When you add your own noise, then you can see the same types of bad behavior for some of things like ransack. And here are the black and blue curves that I mentioned between our algorithm and the Lai, Rao, and Vempala. One of the neat things is you can also do this experiment and think about a covariance which is really distorted along some axes. So you can think about some axes which it has variance 10 and others where it has variance 1. Those are things which are much further from being isotropic. That's the anisotropic case. And there, the fact that you really want an algorithm which has affine invariant guarantees shows out. Because in fact, some of these other guarantees, for example, of Lai, Rao, and Vempala, they work much worse in the anisotropic case because of how the way that they're using to measure closeness between sigma hat and sigma depends on the affine transformation you apply to the data, how stretched out some axes are compared to others. Now I can tell you my favorite experiment in this, which is all of these things were synthetic experiments. There were ways of understanding how bad is the dimension dependence for the existing estimators. We know that no one had proven anything that was dimension independent, but those experiments showed us that they really were that bad empirically. But now this notion of, the inliers, the uncorrupted points as being Gaussian, was really just an approximation. It was some notion that what makes the problem of computing the Tukey median hard is the fact that the adversary sets up your entire problem. They choose where the inliers are, they choose where the outliers are. But once you have some sort of regularity conditions about how the inliers are well distributed in space, it becomes a lot easier to localize the directions where the outliers have been added. So now let's test out that assumption that we had built in, that some of the things that we proved, maybe they're not actually all that specific to the data being Gaussian and they have broader relevance. So here I'm going to take this famous genetics experiment due to November et al. It's a beautiful experiment. What they did was they took this NIH data set, the Papyrus project, and they used it. These were all individuals who'd been fully genetically sequenced, and they used that data to construct a matrix. So this matrix is people by SNPs. So SNPs are the location in which you have genetic differences. And so they took this gigantic matrix of people versus genetic information, and they took the top two singular vectors of the matrix. And what you then do is you project the data onto those two singular vectors. And this is what they got, where they've color-coded each of the people with where they're from, what their country of origin is. So what we're really doing is we're looking for the two directions of largest genetic variation, and it turns out that what you get is actually the map of Europe, which is kind of amazing. So this is usually called genes mirror geography in Europe. It makes a lot of sense when you think about it, but it's surprising the first time, is that the directions of largest genetic variation ought to be geographic. For example, what thermocline, the average temperature in a given location, ought to be one of the biggest drivers behind genetic variation. So this was a really neat experiment. But one thing I should mention was that they had to make sure that all of the individuals that they included in this study were very carefully pruned. So in fact, they only included individuals in this study which had a very well-defined notion of their geographic location. So they were only people for whom all of their 4 grandparents were from villages within 50 kilometers of each other. So they had to remove all notions of immigrants or people who'd been transposed from one part of the population to another in order to get this kind of nice map. So as I mentioned, there was this giant vacuum in robust statistics, that there was no empirical studies to test out which estimators are better than which ones. But here, one thing we can do is we can make our own experiment. So what if I take this data set that's well known and loved within the genetics community and I add my own noise? I can study things like how badly does that noise affect the things that I find. So in fact, we did the same type of thing, that we added 10% random noise along a random direction. And what happens is that when you add this 10% subpopulation that's correlated along a totally different direction, then you can rotate your singular vectors very badly, to the point where then if you do something like naive PCA, you get something that looks nothing like the map of Europe. So if you had just this 10% of noise in your high-dimensional data, you would never be able to find these kinds of genetic phenomena that exist within your data. It's totally been obfuscated from you. We can try it empirically with things like RANSAC do. They also do pretty badly in finding this map of Europe. There are other approaches. There are things like robust PCA, which are formulated in a slightly different way, which there are approaches based on semi-definite programming that do the trick. Usually those things have ingrained assumptions about the rank of the uncorrupted matrix. So the way that they hide a dimension dependence in their robustness guarantees is that they get a lot worse dependence, they get a lot worse error guarantees when the rank of the matrix is larger. And for all of these empirical things, when you take a covariance matrix, there's never a well-defined notion of rank. The spectrum always smoothly decays. And you see this kind of phenomenon in what they can find. But what we can do is, the data is not Gaussian by any means, but we can pretend it's Gaussian. We can pretend it's Gaussian and robustly fit its covariance in a way that's resilient to this 10% noise. And when we robustly fit its covariance, we can then take the top two singular vectors of this covariance sigma hat and then project our data on that. And what we find is almost the same map of Europe that people found to begin with, even in the presence of these 10% corruptions. So this is a nice visual way to think about how not robust some of our known and beloved techniques, something as pervasive as principal component analysis is, how badly they can depend on the dimension and how in the things that they find, versus there are new approaches to these types of problems that really utilize the fact that you can be both computationally efficient and provably robust under somewhat reasonable assumptions. Now I should mention, yeah?
Just to understand the result, so what you're saying is you use your unknown covariance feature
Yeah.
to do the projection, to modify things.
Exactly.
And then you ran PC on what you want.
Yeah, that's right. Exactly. Exactly. Yep.
How do you get these 10% of
Same thing, so we just choose a random direction. We add 10% noise correlated along that direction in a way that it's on this thin spherical shell. So that way the norm of the noise, the points of the noise, is the same as the norm of the signal. So you can't just naively prune it out. It's the same way that in that picture that I showed you where I added those red points in some direction. It's only the fact that you can't figure out which points are black and red, because along those points you do have inliers too. It's just that when they're all ganging up on you in one direction, then you can find many of them. So it's the same type of deal. Yep. What? What do you mean?
So here you're adding noise to the pool data set, right? They can do pruning of data, right?
Sure. Yeah.
So you could just use the entire data set. Don't prune, right? And
Oh, yeah. So that's a good question. So it turns out that the NIH will not give me certification to do that. So you need to pass all sorts of NIH certifications to do that, but they're not typically set up for mathematicians to get access to the data, so I have yet to get access to the unobfuscated data. So the only things that I have access to are the ones which are able to reproduce the November et al. Types of things. The full data set is absolutely not available. So it's hidden behind NIH walls, but it's a lot easier to get access to it if you're a part of like a biology institute like the Broad, but it's more tricky. Yeah, I'm not sure. So actually one of my students told me that he found it illegally, but we haven't used that one yet. Yeah, I don't know. I didn't feel like asking follow-up questions to that. I should also mention we lost Turkey. So you see this like 4 constellation of dots down here is Turkey. Now to be fair, this is really a data set with about 1,300 data points. So it seems reasonable that you lose a little bit on these things, and they are somewhat outliers in the original projection. But these singular vectors that it finds are actually quite close to the original ones, which is pretty neat. So let me at least mention some more philosophical things that I think are neat things to think about. And actually in whatever remains in this talk, I'm going to take a slightly different tact about robustness. And instead of asking what algorithms can do for being provably robust, I'm going to ask what robustness can teach about algorithms that we know and love. But in any case, one of the things that I find really exciting is that if you look back in some of these classic works in robust statistics, there's always this debate about what's the value in having provably robust things? Could you instead just look and find the outliers yourself? If you think back to the original example I gave you where you needed the empirical median as opposed to the empirical mean, well, if you really did see a blip all the way out in the tails of your data set, you would just remove those because those are probably outliers. So there are a lot of famous examples. One of them was something called the speed of light data set back in the day, where one of the great successes of robust statistics was that they were actually able to figure out where the outliers were and go back through and trace and figure out that those honestly were machine failures in the collection of some of the scientific experiments. But this sort of tension about what is robust statistics good for, besides things that you can do more ad hoc just by looking at your data and pruning things heuristically, I think this makes a whole heck of a lot more sense in high dimensions. Because then you're talking about situations where when I add some subpopulation that's correlated along some hidden direction, you can't actually visualize your high dimensional data sets, so you can no longer eyeball and pick those things out. In fact, what's worse is if you try and visualize your data set by projecting it randomly in a bunch of different directions, everything contracts by exactly this root D factor, which is where this root D factor came from, and that means that it's still hard to find those directions where the outliers live. So in fact, for a lot of the data sets that we know and love, we don't actually know to what extent the data analysis things that we're doing on them are corrupted by some small subpopulation that we don't understand. In fact, once I had to give this talk to a scientific audience, and the way that I wanted to explain why these things are somewhat universal questions that a lot of people should care about was I explained it as, we all know that real data is noisy. So what do you do when you're faced with an actual data science question? The first thing you would do is you would try and clean up your data set. But how do you know that you did a good job? So if you clean your data set, the first thing you might do is compute the empirical mean and the empirical covariance to get a rough handle on what's going on. But how do you know you did a good job? And there's not 1% of your data you could remove that would change your answer drastically in some direction, that could change your covariance, your variance along some direction by a factor of 100. You don't know. And that's a little bit of a scary proposition for all of the things that we rely on. PCA is one of the bread and butter tools. If we don't know that, what kinds of phenomenon in high dimensional data sets are we missing? In fact, this issue is so pervasive that when I gave that talk, someone actually made a wager with me that their algorithms already solved this problem, because it was just unfathomable that the things that we're building all of our scientific knowledge on could be vulnerable in these ways. But they are. So one of the things that I think is really exciting too is that what's really going on underneath this is that what we really have is we have a way of finding the non-Gaussian projections of data. That's really what we're doing when we're doing all of these tensor spectral approaches based on Isserlis's theorem, is we know what the moments of a Gaussian look like. We know how they relate to matchings and how they relate to restricted eigenvalue conditions. What we're really doing is we're using that technology to turn the question of looking for a direction in which the fourth moments are really off from what they should be into a problem that you can algorithmically solve through spectral techniques. So this basic idea of, it's not just removing noise that's been added to your data, it's also a question of just exploring the high dimensional data sets that you have. In fact, a lot of high dimensional data sets, when you project them randomly, they look Gaussian. So in fact, the things that you're really looking for to get a handle on what the data set looks like is what are the projections that look really non-Gaussian. So one of the things that I want to think about going forward is how to use these types of tools for exploratory data analysis. What can taking real-world data sets and looking for the non-Gaussian projections teach you? One of my favorite examples is within biology, there are these things called the consortium projects, like the ENCODE project, where what they do is they have some giant NIH initiative that they want to do things like genetically sequence certain types of mice. So they send out this consortium call to all of these different labs who then participate in these experiments, and they all pool their data together to collect some sort of good snapshot of what they wanted to learn. But there are all sorts of empirical studies within computational biology about how much the particular data collection process affects the data that you find. There are literally examples where it depends on this postdoc shakes this beaker 3 times, and this grad student shakes it only twice. And that little change can actually drastically affect the things that you find. So in these types of examples, we don't understand to what extent lab-specific biases in the data collection project affect the overall results we found. So how valid are the scientific conclusions that we derive from these consortium experiments? In fact, one of the neat things you could wonder is, and this we're still working on, is whether you can take these data in these ENCODE projects and maybe by looking for non-Gaussian projections, you would find the directions in which the data stratifies into which lab collected which data. And if you could reverse engineer which lab collected which data, then that would tell you a heck of a lot about how much trust you can really place into the process. So in any case, what I claim is that this is really what I think robust estimation of high dimensions would have been doing all along if they had computationally efficient tools, is they would really be using it as a way to visualize and understand these high dimensional data sets. Not just noise being bad, but as a way to wrap your head around what's actually going on in high dimensions. So the very last thing, which I have a little bit of time to talk about, is that there are really many facets to robustness. I want to give you a little bit of a taste of some other facet of it. So robustness is not just the goal in its own right. Yes, I want things that are provably robust and also computationally efficient. It's also a great way to revisit the things that we think we know. So in fact, I want to tell you a little bit of a story. This one's a little bit more of a sort of developing story, but I'll give you one example of how thinking about robustness as a goal can teach us, can upend which algorithms we think are better than which other ones. So let me tell you a story about the relationship now between robustness and algorithms, but robustness and statistical questions, things like sharp thresholds in inference problems. And the story goes back to one of the classic models, which is called the stochastic block model. So the stochastic block model is this old and storied model that goes back to Holland, LASSIC, and Leinert, which is a random graph model for studying things like how do you detect communities, well-connected subgraphs within a much larger graph. So the way that you do it is you think about k communities, and there's going to be, the original graph is going to be partitioned into these k communities, so each node has a different hidden color. And then you have a k by k matrix of different connection probabilities, which just describes if you have a given pair of nodes, if one belongs to one community and the other one belongs to another, what's the probability that they're going to be connected by an edge? So once you've chosen the community assignment and the connection probability matrix, all you do is you independently sample edges according to this k by k matrix. So in fact, this model is so pervasive and fundamental that it's been studied not just in statistics, but also computer science, information theory, and more recently in statistical physics. And this is going to play a key role in what I tell you about. So in fact, it's become a type of test bed for a lot of diverse algorithmic tools. The basic question of, given a sample from a stochastic block model, can you design algorithms that reverse engineer what the community structure is from the graph? So some of the first things that were invented were just combinatorial methods, things like degree counting to figure out who belongs to the same community and who belongs to different communities with provable guarantees. Then there were all kinds of spectral techniques where instead what you do is you take your graph and you form an n by n adjacency matrix, and the top k singular vectors will actually tell you a whole heck of a lot about which nodes belong to which communities. There were other techniques like MCMC techniques. There were semi-definite programs instead. And all of these algorithms really, they succeed in some range of parameters where they're able to recover the community structure. So some sorts of parameters about what the connection probabilities are and how balanced the communities are. But lately, there's been a revival of interest in some of these fundamental questions about asking, can we reach the information theoretical limits of when it's possible to recover the community structure? So that's the notion of sharp statistical thresholds, and I'll bring in robustness later on. But first I want to tell you some of the classic results here. So there was a beautiful conjecture due to Dessel et al., which studied the simplest version of the stochastic block model. There's only two communities and they have equal sizes. And let's say that the connection probabilities within a community are A over n. Think about A as being a constant. And the connection probabilities between communities as being B over n. Again, B is a constant. So you can ask the question, when can you recover the community structure? Now the first thing that I want to mention is that you're not actually in these situations, you're not always trying to recover with high probability the entire community structure. Because if you think about A and B as being constants, then actually the degree of a node is a Poisson random variable, so you're going to have a bunch of isolated nodes. Those are nodes that aren't connected to anyone, so there's no chance to discover which community they belong to. Instead, the way that they set up their question was they just wanted to find a partition, a bisection of the graph that had non-trivial agreement with the true one. So something that agrees with 51% of it. So you take your algorithm, you spit out a bisection, and in one of the pieces of the bisection, 51% of the nodes are blue, and the other one, 51% are red. And that's called partial recovery. And they made this beautifully sharp conjecture, which, as a theoretical computer scientist, I'm usually pretty lax with constants. I'm even pretty lax with polylog terms. But they made an incredibly sharp conjecture down to the darn constants. They said partial recovery is possible if and only if a minus b squared is larger than 2a plus b. And this conjecture is actually based on this amazing heuristic called belief propagation, which, let me tell you a little bit about belief propagation and how they came to this conjecture. So belief propagation was invented by Judea Pearl and collaborators in the 1980s. And Pearl even won a Turing Award, in large part for belief propagation and more generally for laying the foundations for probabilistic and causal reasoning. And what belief propagation is, it's a general algorithm, but you can think about it just in the context of community detection. It's just some iterative algorithm where nodes maintain beliefs and they update their beliefs from talking to each other. So you start off with any node has some distribution on, he thinks he belongs to the first community with some probability. He belongs to the second community with another probability, and so on. And what happens is that in one phase, every node sends their probabilities of their beliefs to everyone else. And then what you do is you update your beliefs because, if V really strongly believes that he's in the first community, but then I don't have an edge with V connecting to V, I might slightly downweight my belief that I belong to the first community myself because it's a little bit less likely than I am. So there's some sort of explicit update rules that you can write down for this. And all you do is you iterate this until convergence. That's belief propagation. So in fact, belief propagation has a trivial fixed point now where you could get stuck, which is the situation where no one knows anything. What happens if every node believes that they're equally likely to be in the red and blue communities? That means essentially I know nothing, and when you communicate with the other nodes, you get stuck at this one fixed point. So if no one knows anything, you never update your beliefs because no one taught you anything. So in fact, this conjecture of Dessel et al., where it came from, was really a study of the fixed points of belief propagation. So what they studied was when is this trivial fixed point stable? So if you perturb away from it, when are you likely to be brought back into that one fixed point versus repelled along some other direction? It turns out that you can use some local approximation in Taylor series and figure out that this fixed point is unstable if and only if a minus b squared is larger than 2a plus b. So in fact, all of this conjecture was based on this incredibly optimistic chain of reasoning that they usually believe within statistical physics that belief propagation is the ultimate algorithm. It's the best possible algorithm you could hope for in a Bayesian problem. So what they believed was that, well, if belief propagation doesn't get stuck at the trivial fixed point, then whatever it gets stuck at eventually clearly is going to solve the partial recovery problem. And so the problem is solvable. And in fact, even more boldly, when it does get stuck at this trivial fixed point and belief propagation doesn't work, it must not be a fault of the algorithm. It must be because the problem is information theoretically impossible. This was the chain of reasoning to arrive at this conjecture. But the really amazing thing is that this conjecture turned out to be true, as many of the conjectures in statistical physics often turn out to be. So Mossel, Niemann, and Sly, and Masuli independently proved that it's possible to find a partition that's correlated with the true community structure if and only if a minus b squared is larger than 2a plus b. So at this point in the story, I was quite confused myself because, as a theoretical computer scientist, belief propagation isn't my go-to algorithm, or even the linearizations of BP that they were using with no non-backtracking walks were not the usual things I think of, because you can't even solve them with convex programming relaxations. My first attempt would have been based on semi-definite programs, which, broad swaths of theory will tell you that that's about the best you can do for a large variety of problems, things like the unique games conjecture. But amazingly, approaches based on semi-definite programs were not able to get down to those same sharp constants. They could get partial recovery if a minus b squared was larger than ca plus b for some constant c that's strictly larger than 2. So at this point, you have to do a lot of soul searching. You wonder, as an algorithms person, maybe all algorithms researchers should have to learn belief propagation, because it should just be one of our tools in our toolkit if it's doing something that really just can't be achieved by semi-definite programs. So maybe these non-convex approaches are just better than some of our convex programming approaches. And the other sort of meta question that was always on my mind here is that belief propagation is a way of making predictions about various problems. Predictions about where the problem is information theoretically solvable, where it's not, where it's computationally solvable, where it's not. You can do all of this through the idea of fixed points of belief propagation. But within theoretical computer science, we have our own formalisms for making predictions about where problems are easy or hard. When we don't have the theory of NP hardness and reductions, a lot of times we use lower bounds against convex programming hierarchies as a form of evidence. So how do these different forms of evidence relate to each other? When all of a sudden these worlds of theoretical computer science and statistical physics are colliding and talking about the same problems, do we make the same predictions? And if we don't, who's right and who's wrong? So it turns out that robustness is going to play a key role in the answers to these questions, because they're a lot more subtle than you might think. So I want to introduce this last character, which is this notion of semi-random models. I think it's a beautiful idea, which was introduced by Blum and Spencer and refined within Feige and Killian. It's a neat way to test the robustness of your algorithms. It's a little bit different than the types of things I showed you before. So instead it works as follows. The first step in these models is you sample something from the stochastic block model. Same as before, we can think about a planted bisection problem with connection probabilities A over n and B over n. But now what happens is you add an adversary, but this adversary is only allowed to make helpful changes. So what they're allowed to do is they're allowed to delete edges crossing the bisection and add edges within one of the bisections. So all they're doing is they're making a community better connected, or they're destroying some of the connections between the two communities. In principle, this sounds like it should only make your life easier, because your goal is to find these well-connected substructures within it. That's what I mean by the adversaries being helpful. All of these changes are monotone. But it turns out that the advantage of studying it in these kinds of formalisms is that your algorithms can no longer tune to a very particular distribution. So when you talk about random graph models like Erdos-Rényi or random graph models like the stochastic block model, they tend to produce random but very rigid looking random objects, because all the nodes have about the same degree distribution, and they all have nice expansion properties, and they look very homogeneous in many ways. But these types of changes that the adversary is allowed to make, while making your problem intuitively easier, they destroy some of the sharp regularity, which might be the thing that your algorithm is overexploiting to make itself work. So it's a great way to stress test your algorithms to see, are they working for brittle reasons or more fundamental reasons? So just to give you an idea about how these types of things work, let me give you an example of a non-robust algorithm and how you can break it with a semi-random model. So imagine I consider this bisection problem where within each community I connect nodes, I'm in a dense setting. The connection probability within a community is a half. The connection probability between communities is a quarter. So what I can do is I can take, if two nodes belong to the same community, I can calculate the expected number of common neighbors that they have. So if the two nodes belong to the same community, then if I choose a random other node in the graph, there's about a half chance, there's n over 2 of those other nodes essentially, that belong to the same community as they do, and you have a half squared chance of that new node connecting to both of them. And if it's on the other side of the partition, then you have a quarter squared chance. Now you can do the same calculation in the case where you have nodes from different communities. When you have two nodes from different communities, there's only one possibility that any other node you look at is in the same community as one and a different community as the other. and then you have a half times a quarter chance that you're connected to both of them. But the important thing is just that this top quantity is larger than the bottom one, so this gives you a very simple combinatorial algorithm. All you do is for every pair of nodes, you count the number of common neighbors, the number of nodes which are connected to both of them. If it's above some threshold, you declare that the nodes are in the same community. If it's below it, you declare that they're in different communities. And that works with high probability. But it's also something which is incredibly brittle to your modeling assumptions, because it uses not just the connection probabilities between nodes, the connection probabilities within a community versus between a community. It also relies on counting how often you have these other nodes on the other side that belong to a different community. So you're using not just the structure of the signal of which nodes belong to the same community, but also the structure of the noise about how often they have a common neighbor who's actually in a different community. So instead what you could do is your monotone adversary could just boost the connection probabilities on one side of this community structure and make them all be 1. And then what you can check is that if you take 2 nodes from the blue community and calculate the expected number of common neighbors, that this turns out to go the other way as if the nodes belong to different communities. So in fact, a lot of the algorithms which are designed for the stochastic block model all have these properties that they work only for the stochastic block model, and once you make slight changes to the distribution, even ones that sound intuitively like they ought to help you, they turn out to break the algorithms. So in fact, one of the neat results that I want to tell you about along these lines is that, so it turns out that not only can these monotone changes just break these laundry list of algorithms that are out there, things like belief propagation and combinatorial algorithms, it turns out that actually it strictly makes the problem information theoretically harder. So it's a kind of surprising fact, but this helpful adversary that's making a community better connected and destroying connections between communities can actually move the information theoretic threshold. So even when the constant C is 2, it no longer becomes possible to recover the underlying community structure. So what this means is a really strong statement that not only do algorithms like belief propagation that reach the information theoretic limits of the problem break when you add monotone changes, in fact, all algorithms that reach those sharp thresholds break. That the only way that you can reach those sharp thresholds is not just by exploiting the structure of the signal, but also the structure of the noise. And one of the neat ways that this explains how the worlds of theoretical computer science and statistical physics collide, it tells you, how to vindicate STPs, why it's okay that they don't reach the sharp information theoretic thresholds. Because semi-definite programs actually turn out to continue to work in semi-random models. So what this means is that belief propagation is often a very sharp prediction about one and only one distributional model, whereas things like semi-definite programs tend to be predictions about entire families of distributions, all of the distributions you can get under these monotone changes. So it's a neat way in which, taking even well-defined statistical models where you study the efficacy of algorithms, adding in some modicum of robustness can really change which algorithm you think is better than which other one. So the last thing that I would conclude with is just a little bit of a philosophical question here, which is that, usually these semi-random models, they were introduced in theoretical computer science as a way of studying beyond worst case analysis, as a way of taking problems that are hard in the worst case and thinking about, making them a little bit easier and still trying to solve them. But usually I like thinking about them instead as a way to stress test how robust the guarantees we have for various algorithms working on distributional models really are. Yep.
Semi-random model was about the helpful.
Yep.
So what about the slightly unhelpful? Cannot be too unhelpful.
Right. So the reason I phrased it this way is you can definitely study things like, the adversary just making a bounded number of changes, period, depending on, right. But there it would be much more obvious that it moves the information theoretic threshold because they could just remove some of the signal. So here the thing that's much less obvious is that when the adversary is only allowed to make monotone changes, that it actually still affects the statistical thresholds. So what that really means is that the statistical threshold is not just about the signal present, about where the well-connected communities are, but it's also about properties of the noise, because you have to use how often you end up connecting to nodes on different sides to exactly reach the information theoretic limits? That's a great question. We can take it offline if you need more discussion. But the thing that I want to mention is that, in a lot of cases we have algorithms which, things like STPs, which have worse performance guarantees when you talk about running them on stochastic block models than other algorithms that do better in these simple average case models. We can ask the question, why are they preferred? Well, what I claim is that these models that we study, whether they're worst case or average case, are really just measuring sticks for our different algorithms. And in a lot of cases, we're missing different axes on which to measure these algorithms. So these semi-random models give us a different way of figuring out which algorithms are better than which other ones, because it's not just about reaching the information theoretic thresholds, but doing so in a way that its performance degrades smoothly. So let me, I guess, close with, usually I like thinking about these semi-random models as not being about worst case analysis, as making the problem just a little bit easier so that we get around computational intractability, but as a way to move above average case analysis. So as a way to slightly change our average case distributions and understand which of our results do and don't translate. So that's a direction in which I think a lot of our understanding about when we can do non-convex optimization in average case settings, we don't really have a good understanding of which of those algorithms have good guarantees outside of those very particular distributional models. So I'll end there and ask whether, and give you a quick summary of the talk. So what I hope you got out of this talk was I started off by talking about some of the basic questions in robust statistics about the problem of giving high-dimensional estimators that are both provably robust and computationally efficient. So this was about understanding the facet of robustness where we want algorithms to be provably robust. And then I gave you some neat applications to genetic data, and I wonder whether high-dimensional practical robust statistics is within reach. And then towards the end of the talk, I also talked about robustness as a way to augment or stress test the guarantees we have for algorithms in average case settings and understand whether the types of theorems we have meaningful guarantees beyond those very particular models we've been studying. So let me end there, and thanks for your attention, and happy to take any questions.